Welcome to a session on critical phenomena. In this session, we will be seeing critical constants, critical phenomena, Andrew's experiment and the continuity of states. Now, let us move on to the topic. First, we will see critical constants and critical phenomena. Now, if we have a gas, that is, if a gas is taken, now what we are going to do is to liquefy a gas, we will have to lower the temperature as well as increase the pressure. So, these two combined effects, what happens is the gas will get converted into liquid. Now, critical state, what we are going to consider is, it is the condition, it is a critical condition you can say, that is a condition at which the gas just gets transferred or converted into liquid or the otherwise. Now, we have two options, that is, we have to decrease the temperature as well as increase the pressure. Now, what happens when we decrease the pressure? A decrease in temperature, first we will see what is a decrease in temperature. When we decrease the temperature, the kinetic energy of the molecules decreases. That is, kinetic energy of the gas molecules decreases. Once the kinetic energy is decreased, the velocity with which the molecules are moving decreases and they start coming closer and closer, which means that there is a decrease in volume of the gas. Now, that is the result. Second point, there is a decrease in volume of the gas. Now, again, once the molecules they come closer together, what happens is their intermolecular forces of attraction plays a bigger role, that is, it keeps on increasing, they get attracted to each other and the gas finally gets converted into liquid. So, there are three factors. One is decrease in kinetic energy, and as a result there is a decrease in volume because their velocity decreases, there will be a decrease in volume and there will be an increase in molecular interactions. Okay. Now, next point what we have been saying is that we have to increase the pressure. Now, when we increase the pressure, what happens is there will be decrease in volume. So, that is, there is a decrease in volume, that is the point we can represent it as decrease in volume. There is the same effect which we got when we decreased the pressure. So, when we decrease the temperature. When we increase the pressure, there is the same effect, that is volume is decreasing. Now, when volume decreases, naturally what happens is the molecules come closer and there will be an increase in intermolecular attractions. So, these two factors, that is decrease in temperature and increase of pressure, both together, what happens is the molecules come closer, intermolecular force of attraction increases and the gas gets liquefied. So, these are the main two factors. Now, one more point to be noted is that it has been found that even if the temperature of the gas is lowered, okay, and high pressure is applied, the gas gets liquefied, we will say like that. But effect of temperature is more prominent than effect of pressure in liquefaction of gases. This is a very important point, that is, effect of temperature is more important than effect of pressure in liquefaction of gases. Now, so what happens is, in some cases you can see that you give a certain temperature and however greater pressure you apply, the gas never gets liquefied. Now, it has been experimented and it has been found that for every gas there is a certain temperature. Only below it or at that particular temperature you can liquefy the gas. Any temperature above it, if the gas is above that temperature, however high the pressure you apply, you can never liquefy a gas. Okay. So, that condition is known as the critical temperature, and by definition the temperature at or above which a gas cannot be liquefied at or above which, see, you will have to take it at or above which the gas cannot be liquefied regardless the amount of pressure applied. Even you can apply very high pressures, still the gas will never get liquefied, and this temperature is known as critical temperature, or it is denoted as T with a subscript small c. Okay. And it has been found that experimentally, actually it was done for carbon dioxide, and for carbon dioxide it has been found that the critical temperature Tc is 31.1 degree Celsius. Okay. Next is the condition of pressure. So, temperature is the most prominent factor, and that temperature, minimum temperature, that is you have to have until unless you can liquefy a gas by applying pressure. Any temperature above that, it will not work, or it will not never get liquefied, and for carbon dioxide is 31.1 degree Celsius. Now, the pressure you have to apply at that critical temperature to liquefy a gas is known as critical pressure, and that pressure can be any value, but the thing is there should be a minimum value for the pressure required to liquefy the gas at critical temperature is known as critical pressure. See, it is a minimum pressure, it is very important, it is a minimum pressure. You can apply any pressure higher than that, it is a minimum pressure required to liquefy the gas at its critical temperature is known as critical pressure, and it is denoted by the letter capital P with a subscript small c. And for carbon dioxide at critical temperature of 31.1 degree Celsius, the pressure has to be applied as 73 atmospheres. Now, if you have critical temperature and pressure, naturally we will have critical volume, and critical volume is nothing but it is a volume of 1 mole of a gas occupied at its critical temperature and pressure. So, it can be defined as the volume occupied by 1 mole. It is the molar volume of a gas at critical pressure and critical temperature is known as the critical volume, or it is also known as critical molar volume, because we know that that is for 1 mole. So, that is for 1 mole, it is very important, at Tc and Pc. So, 1 mole under the critical temperature and pressure condition, and for carbon dioxide Vc has been found to be 93 centimeter cube, or you can call it as Cc. Now, these constants, that is critical temperature, critical pressure and critical volume of a gas, are known as critical constants. So, these things are known as critical constants. Okay. Now, the phenomenon of smooth emerging between the gas and the liquid state at critical state is known as critical phenomenon. So, that is critical phenomenon. That is, it is a smooth merging. That is, you can't find out a separation between the gas and liquid, and that condition is known as critical phenomenon. That is when temperature is Tc, pressure is Pc, and we have the critical phenomenon taking place. Now, let us assume a gas enclosed in a vessel. So, that is we are having a gas enclosed in a vessel. Okay, suppose. Okay, suppose this is a gas, I am not going to mark it. Now, this gas, we have kept a somewhat higher pressure for that gas, it is enclosed in that, and you are going to increase the pressure within the gas to a somewhat high pressure. Now, after this, the pressure is kept constant and we are going to lower the temperature. So, now what happens is, here we will be having gas filled within the vessel, and when the temperature correctly approaches the critical temperature, what happens is there will appear a meniscus in the, that is, which shows that the gas is getting liquefied. You can see the appearance of a meniscus, and meniscus is for liquids, and therefore a liquid meniscus appears and the gas is getting liquefied. You can do the reverse case, that is, here what we have been doing is we have been lowering the temperature. Now you can do the reverse case. Once the gas gets liquefied, you keep on increasing the temperature and you will get a stage at which the meniscus disappears, which means that there is no more liquid within the vessel. Clear? So this is interconversion between the gaseous state to liquid state and liquid state to gaseous state, and there is a particular region in between, that is at that particular time when the meniscus starts to appear, and this is the temperature which will be corresponding to its critical temperature, and the pressure corresponding to that will be the critical pressure. Okay. Now let us move on to Andrews experiment. Now in the beginning, some of the gases, it has been found that like hydrogen, helium, then some of the gases like hydrogen, helium, etc. When this has been, they try to liquefy these gases, it has been found that they couldn't liquefy it. So they were considered as permanent gases. Until unless there was an experiment conducted by Andrews regarding what he did is he took carbon dioxide and he studied the curves, that is the liquefaction of carbon dioxide at different temperatures. Now you can see from this picture, see this is the curves, that is the first one is at 13.1 degrees Celsius. This is the first one which is shown in this blue color, that is the temperature is 13.1 degrees Celsius. Now you can see that is you are having carbon dioxide. Now one more thing to be noted is this is a plot against pressure and volume. You are having higher volumes means that is in the gaseous state, here the volume is greater, on the other side the volume is decreasing, that means that might be the liquid state, and pressure you can see it increases upwards. Now if I have taken a gas at this point, suppose, okay, this is at this point I have taken, and the volume corresponding will be this volume. Okay. Now what I am going to do is I am going to apply apply pressure so that its volume is decreasing. Temperature is maintained constant at 13.1 degrees Celsius. Okay. Now what I am going to do is I am going to apply pressure, means the pressure is increasing. Now here it moves along this point up till the point Y. Till the point Y. What is happening? The gas is being compressed because pressure is increasing, the gas is getting compressed. So what happens is its volume is keeping on decreasing and it reaches the point Y, where just I told you that is the appearance of the meniscus occurs, that is the gas gets liquefied, not wholly but part by part it is getting liquefied. So first liquid appears at the point Y. Now from Y to the point X, you can see that even though we are increasing the pressure, the effect is not felt there. See, there is no increase in pressure, but there is a decrease in volume. What is happening? The gas is getting converted into liquid form, and naturally the volume decreases, because in the gaseous state the molecules are far apart. When we come to the liquid state, the molecules are closer together, and as a result the volume is decreasing, and up till this point at the point X, the whole of the gas is getting converted into liquid. So the region X to Y, that region you can see that is a place where we have the liquid as well as a gaseous state coexisting. Okay. So, at Y liquefaction starts, some of the gas gets liquefied and the liquefaction continues till the point X where the whole of the gas gets converted into liquid, and then what happens is we are again increasing the pressure, and you can see there is no much change. There is a slight change in volume, but not much change in volume, showing that liquid is not compressible as gas. Okay. So, that is the explanation for the isotherm, PV isotherm for carbon dioxide at 13.1 degree Celsius. Now, let us move on to the next temperature, and remember that is the critical temperature is, if you remember, it is 31.1 degree Celsius, that is the point here, and the pressure is 73 atmospheres, which is written here, that is 73. This is 73, okay, and this is the temperature 31.1 degree. So, now this all these temperatures we are considering is below the critical temperature. 13.1 degree is below the critical temperature. Now, next is 21.5 degree Celsius. Now, that is shown by the red color. The other one was blue, this is in somewhat red or pinkish shade. You can see that at the point A, here it is marked A, at the point A you are having the gas, it is totally in the gaseous state. Now, we are going to apply pressure or compress, the volume decreases till the point B. Now, just like as in Y, at the point B, what happens is liquefaction starts, and from this you have the liquid and the gas coexisting, goes up to the point C where whole of the gas is getting liquefied, and from point C again you can see there is no much change in the volume with such an increase in pressure, because liquid is not that compressible as that of gas. Now, let us come to the critical point, that is when the temperature is 31.1 degree Celsius. So, that is shown by some bluish color, this thing, that is the temperature they have written is 30.98, but here we will be using it as 31.1 degree Celsius, which is approximately equal to 31.1 degree Celsius. Now, at that temperature you can see that it is in the gaseous state. Okay. Now, I am going to increase the pressure, the gas goes on decreasing in volume, and at that particular point 31.1 for 1 degree Celsius, that is when the pressure corresponds to 73 atmospheres, on a sudden the whole of the gas gets converted into liquid. So, there is no transition, you can see that up to that point it is totally gas, and just after that point you have only liquid, and you do not have any discontinuity. You can see that in the other two cases there is a discontinuity. See, for the first one 13.1, that is you are having a discontinuity where we have both, here you will be having gas plus liquid. Here up till this point you are having only gas, at this point you are having a liquid, and this is a region where we have the discontinuity, where we have both gas and liquid coexisting. Now, in 21.5 also you have a region that is from B to C. This region you have a discontinuity because you have some of that gases being liquefied. So, you have liquefied and also liquid in contact with the gas. So, there is a discontinuity, and you can see that at the point C what happens is it is completely converted into liquid. So, there is a separation between the liquid state as well as the gaseous state, and it is by a region where we have both liquid and gas coexisting. Now, when we come to the critical condition, okay, there at that particular moment, there is a single moment where the pressure is 73 atmospheres and temperature is 31.1. It is an isotherm, so the whole system is at the temperature 31.1, but as soon as the pressure becomes 73 atmospheres, all on a sudden the complete gas is being converted into liquid state without any discontinuity. You don't have that is some of the gas is liquefied and half of it is remaining in the gaseous state or something of that sort. Okay. So, without discontinuity you will get the sudden transformation of gaseous state into liquid state. Okay. Now, when we watch this, one thing we can note that is, see, from x to y, the distance to capital X to y, this distance, and the distance between B to C, you can see that B to C it is lesser. From x to y it is a larger space. Okay. Now, as we go increasing the pressure, you can see the discontinuous region, it narrows. So, what is shown here is it's a curve plotting the region where it will be discontinuous. Discontinuous means there is gas as well as liquid existing side by side. Okay. Now, this region you can see and it vanishes. See, there is a single point at critical conditions. So, this is what Andrews' experiment has shown, and for every gas Andrews suggested that there is a temperature for every gas, so that only at that temperature or below that temperature you can liquefy a gas, and above that temperature whatever be the pressure, the highest pressure you give, the gas never gets liquefied. And therefore, the gases which are considered as permanent gases, they are not permanent gases. It is just because their critical temperature is very high temperatures, sorry, it is not very high, sorry, very low temperatures which are not readily attainable. And therefore, if hydrogen and helium are given sufficiently low temperatures and you apply the pressure, these two gases can be liquefied. Okay. Now, let us see about continuity of states. A gas can be liquefied by applying sufficient pressure at or below its critical temperature. It can be at the critical temperature or any temperature below that. Now, according to principle of continuity of state, so principle of continuity of state, the liquid state does not represent a sharp and discontinuous transition from gaseous state, but it is rather a continuation of gaseous phase into a region of very strong intermolecular attractions and smaller volume. These 2 points very important. That is, according to that, it states that liquid state, it is not a different state or anything. It is a sharp and discontinuous transition from a gaseous state to a continuous gaseous phase into a very strong region of intermolecular attractions. In gaseous state, you know that the molecules are very far apart, they do not have any intermolecular attractions, but when they come closer and closer, the gas is getting transformed into a state where there is very strong intermolecular attractions and smaller volume. Okay. So, according to the principle of continuity of state, liquid state does not represent a sharp and discontinuous transition from gaseous state, but it is rather a continuation of the gaseous phase into a region where there is strong intermolecular force of attraction and smaller volume. Now, let us take another plot of pressure and volume, and here you can see that again you have two curves. The gas is not mentioned, you can take any gas. Now, the first one, that is A, B, C, D, this curve represents any condition, temperature below critical temperature, and the other one which they have shown here, I will represent it as L, M, and N. Okay. Now, this is L, M and N. This is any temperature at Tc. Any temperature means that is for any gas, or you can say rather say it as it is Tc, at Tc. Now, here again you are having a gas represent, this is a gas because we know that the volume is higher on this side. So, do not confuse that anything at higher volume will be in the gaseous state. So, here we are having the gaseous state gas. Okay. Now, this gas at that any temperature, let it be a temperature T, and this temperature T is below critical point. Now, at this condition you can see that as we increase the pressure, see it is moving up. So, the pressure is increasing, the curve moves on to the point B, it reaches a point B. What happens is liquefaction starts. That is the same as starts. Okay. Now, the liquefaction starts here at the point. Now, in this region we have both gas and liquid coexisting in this region. The proportion may vary, but from B to C we have the gas and liquid coexisting together. So, what will happen is if I am taking it in a vessel, you will have, that is here we will have the liquid state where the molecules are closer, and here we have the corresponding vapor of the gas. Okay. Now, here you can see there is a discontinuity, you can see this is different from this. Okay. So, here from the point B to point C, the same gas getting more and more converted into liquid, and at the point C the whole of the thing gets liquefied. So, here we have only liquid state. Now, applying pressure, as I have told you, since gas is liquid is incompressible, it keeps on going up somewhat parallel to pressure axis, or you can say that there is no much change in volume with application of pressure. So, this is a case for this. Now, here this is at the critical point, at the point M represented by the critical temperature. From the point L to M, it will be completely in the gaseous state. At the point M, exactly at the point M, the whole of the gas gets converted into liquid. So, it is in a continuous manner where you can see that at the moment just before M, it is totally gaseous state, and the moment M is reached, it is completely converted into liquid state. So, there is no discontinuity. Now, let us consider you are going to take a gas represented by the point A. This is, we know that it is in the gaseous state. Now, what we are going to do is, I am going to keep the volume constant, okay, volume constant, and I am going to increase the temperature. So, it is going up, temperature is increased. So, what will happen? The temperature increases, the pressure increases, it goes to a point L till the point L is reached. Now, at L also it is in the gaseous state. Now, what I am going to do is, I am now going to reduce the volume. Okay, the volume is reduced. Now, here the volume is reduced, decreasing. How will you reduce the volume? Here you can't change the pressure. So, again here I can say that temperature is lowered. Okay. So, from the point A to L, I have been increasing the temperature. Now, the temperature is increased, the point L is reached. Now, temperature is lowered, automatically the volume is decreasing. Now, it is going like this, and when the point D is reached, you can see the gas has been liquefied. Now, how? The point is, when the temperature is lowered, the volume decreases, and this is the critical condition, and when the line crosses the point N, the whole of the gas gets liquefied, and at D you will be having the liquid state. So, from point A to point D, I have taken the gas, and at the point D you find only liquid state existing. That means conversion of a gas to liquid occurred in a continuous manner. Okay, so that means that gas and liquid, they are not any that conversion is not in a discontinuous manner. Here something we are having in a larger space, that is in the gaseous state. The molecules are brought together either by decreasing temperature or you can increase the pressure. So, the molecules are coming closer and closer. Okay. When at a particular distance, that is the intermolecular distance are decreased, there becomes strong intermolecular force of attraction, and what happens is these molecules stay together and they get converted into liquid state. Okay. So, that is about the continuity of state. And to conclude, in this session we have been seeing critical constants. What are the critical constants we have been seeing? That is critical temperature, critical pressure and critical volume. Critical temperature, what is that? Critical temperature is defined as the temperature at which or above which a liquid can never be liquefied by the application of even high pressures. That is known as critical temperature. Now, what is critical pressure? It is the minimum pressure required to liquefy a gas at critical temperature is known as critical pressure. Now, what is critical volume? There we have to specify, since it is a volume, it is the volume of 1 mole of a gas at critical temperature and critical pressure. Now, critical phenomenon, it is a continuous merging of gas to liquid, or you can say from liquid to gas, whatever it is. It is known as the critical phenomenon where we consider the conditions, that is critical temperature, critical pressure at these temperatures and pressure, that is known as critical phenomena. Next, we have seen Andrews' experiment, who proved that any gas can be liquefied provided that gas is brought to a temperature, that is known as critical temperature, or any temperature below critical temperature. Any gas can be liquefied, and there are no gases such as permanent gases. And the last one is the continuity of state. In continuity of state, we have been trying to prove that any gas can be converted into liquid, and in which we do not say that is a discontinuous process, but you can consider the gas where the molecules are very far apart. They are brought closer and closer by two factors. What are the two factors? That is lowering the temperature and increasing the pressure. So, the gas molecules come closer and closer where the intermolecular force of attraction increases in such a way that these molecules come closer and closer, and they are held together by strong molecular forces. There will be two things: they will be held together by strong intermolecular force of attraction, by which there will be a reduction in the volume too, and that is known as the continuity of states. Thank you, and that is all for this session.